This is a picture or a map done way back in 1973, where the group that did it actually circled all of the areas on Mars where they saw craters. And I hope that, that there's some things that stand out to you in this map right away. That there's some areas that are heavily cratered on Mars. And as you know, when we talked about the late heavy bombardment, that this might represent a period in the Martian history where the surface was heavily impacted. And then maybe in these areas which are kind of intermediate in amount of craters they have, maybe this is an intermediate age where things were happening at this particular time where there wasn't as much activity and things were happening on the surface to destroy what had happened in the past. And then look up there in that clear area in the northeast and the northwest of this map, and you'll see it's very clear of craters. So maybe this is the youngest area on Mars. And that's precisely, and you'll see in this slide, that's precisely what the early scientists that worked on Mars did. They said, hey, look, these older crater areas, we'll call those the Noachian, and we'll say, you know, based on what we know from the moon, they're probably greater than 3.7 billion years. Keep in mind that the bombardment of the moon took place ended about 3.8 billion years ago. So it's not surprising that they put the Noachian at older than 3.7 billion years. And then this Hesperian, which you see there, is that intermediate period. It's still got some craters on it, so it must be close to maybe the heavy bombardment period. So maybe we'll estimate that it was between 3 and 3.7 billion years ago. Now I really have to emphasize that these are estimates. We do not have rocks that have been dated from Mars, so we have to be, very careful in this case. And then we'll call the very young regions on Mars, we'll call that the Amazonian, and that's an area that we'll refer to as less than 3 billion years old. So it's kind of neat that you can take something as simple as craters and get some idea of the history of Mars. But as you can see here, we can go a lot further than that. I have kind of done a chronological diagram here where I have put in the pre-Noachian, because there are two events that we think happened before the Noachian, that is before 4.1 billion years ago. And you'll see in this particular diagram, it looks like there was a gigantic impact sometime before 4.1 billion years ago that scoured out the whole north part of the North Pole. Now, not in the center there. There's actually it did knock it out, but since that time there's been a glacial ice that's formed on the poles. Not only water ice, but also carbon dioxide ice, as you'll see a little bit later on. So we think that's an impact basin. We think that it's a very old impact basin. And the same thing goes for this area called the Hellas Basin. It looks like an ancient impact site too. It's got a lot of craters in it, suggesting that that it happened a long time ago. So those cratering events we're going to call the pre-Noachian. Now keep in mind that this spectacular map was made by the Mars Observer Laser Altimeter, which is shortened for MOLA. And what they did is they basically took lasers and they counted the time it took back to the spacecraft that was going around Mars measuring this, and they carefully calculated the elevations of Mars. So we got this beautiful maps showing us elevations on Mars in great detail in the elevations. So really super stuff, and it helps us to understand the processes that are going on Mars. Well, let's now go and look at the Noachian. I've put dissected by drainage. Well, as you'll see in this diagram, wow, it really was dissected by drainage. Carr in 1995 did this map where he plotted all of the valleys that looked like drainage valleys that were formed by flowing water on Mars. And I hope it hit you over the head. Look at that. It couldn't be nicer. All of the valleys are in the Noachian, and that's the oldest part of Mars. So our conclusion then would be, from looking at this map, that there must have been flowing water on the surface of Mars to create these valleys. And it gets better. Look at this. This is a map, an image of a drainage pattern on Mars, and it's dendritic. Now, look at that picture up in the corner. That's a picture of Tibet, and it's called dendritic stream pattern. And all those are little valleys, and they're all, the little ones are flowing into the bigger ones, and the bigger ones are flowing into the really big ones until you develop these big, big valleys. And that's what we're seeing on Mars. And we know that those kinds of patterns form when we have rainwater and when the surface is about the same hardness consistently through the area. So we think this is good evidence for rain on the surface of Mars. To the north of this image of Mars is there are mountains up there, so the water's flowing from north to south in the direction I put that arrow, and this is the Warrega Vallis, and you can see the water flows from smaller channels to bigger channels until the channel, you can see that area of the circle down there, that's where the stream flows out into what really might be a lake or ocean at the time. It's no longer a lake or ocean. Because it's not down cutting past a certain area, so there might have been water there that it was flowing into. Here's the news. We had rain, it looks like, on the surface of Mars. Let's go back to our chronology now. We have many eroded impact craters that also tell us that it was raining on Mars, and we start to see a bulge called the Tharsis Bulge. Let me show you that right now. Tharsis Bulge over here on the left. Remember, the reddish brown colors are higher elevations. The bluish colors and dark blue, those are lower elevation colors. And that Tharsis Bulge looks like it started to uplift in the Noachian. Now, why do we say it started to uplift in the Noachian? That seems kind of crazy, right? Well, let's take a look at this box that I've filled in there. We're going to do a blow-up of that area. And now we're right on the edge of the Tharsis Bulge. You can see where the mountains are coming up off of the floor there. And guess what? We see drainage on the sides of the Tharsis Bulge. That drainage, again, indicative of rainwater. It's dendritic for all intents and purposes, and it's on the edge of the Tharsis Bulge. So what we think is, we don't see it on the top of the Tharsis Bulge, so what we think is that magmas spewed lava and ash out on the top of the surface, covering up the old stream valleys, but down here on the edges of the Tharsis Bulge, it didn't do that. It didn't destroy the stream patterns. So we're still seeing evidence of those early rains in the Noachian on the Tharsis Bulge. So we must conclude then that the Tharsis Bulge began to uplift and had to be uplifted based on the direction these streams are flowing sometime in the late Noachian, towards the end of the Noachian. Now, as you're going to see here, this is exciting. Now we're into the Hesperian when I'm talking about the upper part of the Tharsis Bulge, which is what you're looking at. The whole area is being pushed up. Now we think it was pushed up by magmas, and you don't have to be a genius to recognize this. I mean, look at those doggone volcanoes there. You've got these monster volcanoes. This one, Olympus Mons, that's the biggest volcano in our solar system. So you had a lot of volcanic activity in this region, so it doesn't take too much to surmise that we had these magmas pushing up from below and raising the Tharsis Bulge. And oh my gosh, look at this. We've got fracturing, just the kind of fracturing we'd expect from an uplift in the central part of the region. Fractures to the north, you can see they're parallel fractures. Fractures in the center, look at all those fractures next to Valles Marineris. And then Valles Marineris, my God, it's a huge rift zone where the crust of Mars has literally been torn open. So big time rifting. I read somewhere, and so don't hold me to this, but I think it's about 8 times bigger than the Grand Canyon. It's just a huge, massive rift zone. I don't mean to imply, by the way, that the Grand Canyon was rifted. It wasn't. But the Tharsis Bulge looks like it was rifted apart. Those fractures support that. The magmas from below are shown on the surface by these big volcanoes. So we would say then that the Noachian/Hesperian is a period of uplift of the Tharsis Bulge, and some really cool stuff taking place, I think, anyway. Now, notice that at 3.7 billion years ago, I put the loss of the magnetic field and perhaps the atmosphere. So let's spend a little bit of time talking about that, because, wow, it fits if you think about it. Mars did have a magnetic field. The first question is, how do we know that? Well, we can take satellites and we can actually look for magnetism in the rocks on Mars. And we find that the magnetism, not magmatism, but magnetism on Mars is, remnant magnetism is frozen in the igneous rocks, the volcanic rocks that came out on the surface of Mars. And so it represents an older magnetic field that once existed. We do this on the mid-ocean ridges. In fact, that's how we discovered that the mid-ocean ridges on Earth were rifting apart. So we looked at the magnetic field, and it mirrors, we'll talk more about this later on, but it mirrors patterns on each side of it, and it can only be explained by rifting. So we had a magnetic field on Mars. We don't see that in the Hesperian. So what the heck? It's probably not a long shot to suggest that the magnetic field disappeared somewhere towards the end of the Noachian. And guess what? Associated with that, we don't see any more drainage outside of the Noachian. We can conclude then that the loss of the magnetic field probably caused the loss of the atmosphere. That would be through the solar winds probably hammering away at the atmosphere. We would have to say then that the Noachian was a warm, wet period on Mars. Rainwater had an atmosphere, and then loses magnetic field, loses atmosphere, becomes a pretty dry place. We also see clays being deposited during this period of time, which are indicative of either alteration or of sediments flowing into an ocean, streams, flowing into an ocean, depositing their fine-grained sediments. So it looks for all the world like we had some really cool Earth-like processes taking place early on Mars. Now we can actually, this is what's so cool, we can actually go down to the surface, and with our rovers, we did this with Curiosity first. This is from Curiosity. Now, that elliptical black field you see there, that's the area that the scientists asked the engineers to set down the rover. And by golly, they set it down right at the cross that you see there in the picture. And that alluvial fan that you also see there, well, I think you might have an idea what alluvial fans are. They occur in arid regions here on Earth, and they're where a channel comes out of the mountains, where it rains in the mountains periodically. You have a big flash flood, comes down, and at the base of the mountain it spreads out, and it deposits its sediment because the water slows down, and you get these big mounds of material deposited called alluvial fans. And we think we're seeing an alluvial fan in front of this valley on Mars. So what do? We try to land there, and we said, if we're going to probably find some cool sediments, it'll be in this alluvial fan. Well, this picture on the left is the exciting result of putting the rover down there and having it drive up and take a picture of a conglomerate. Now, a conglomerate is a rock that's made up of different sizes of particles, all the way from large pebbles down to a smaller size material. And what's so cool about these rocks, both in the debris there and in the conglomerate, is that the pebbles are rounded. What does that mean? Well, rounding, you can think of alteration as breaking up rock, but in order for it to get rounded, they have to travel. The rocks have to travel in a stream, and they bang up against each other. It's like being in a tumbler, and they erode off all of the edges, so you get rounded pebbles. So the fact that we're seeing rounded pebbles on Mars, oh my gosh, it means that they were carried by a stream and deposited. Now also what's really cool, they're conglomerates. That means they're rocks, folks, And in order to have rock, you've got to have groundwater flowing through that rock in order for it to be lithified. Lithified just means that it means it's turned into a rock. So we had the water flowing through it and depositing some sort of cementing agent, which brought the rock and made it solid. Cements can be silica dioxide or calcium carbonate. It just depends on the pH and the EH of the water and what kind of material the water's carrying. But the ultimate conclusion is it's a rock. It's a rock on Mars formed, and it had to be formed, sedimentary rock, by this cementing process called lithification. Take a look at the picture on the right. That's a picture of a conglomerate in an alluvial fan that formed on Earth. So it's not like we can't actually go up and study these things. We can. Now these are some pictures from Opportunity rover. I want to emphasize that this is an outcrop on Mars, and you can't see it very well in the true picture, the colored picture. You have to look at the black and white. I hope you can see there's bedding in those rocks, and the lines, I'm going to show you some lines that I drew in to help focus you on the bedding. Look at the angles on those beddings. They're not parallel, they're slightly at angles to each other, and we call this cross bedding. And the way that we know cross bedding forms here on Earth is through sand dunes. Now think about that. Sand dunes are like this. The wind's blowing from this direction, and the wind will carry the sand up the sand dune, and then they'll drop off suddenly on the sand dune. And then as the wind continues to blow, you'll get a series of sand blowing over the top of the sand dune. And these sand dunes move across deserts, literally move. And you can have sand dunes run into each other. And so at the end of the day, when these things get fossilized, they look like you're seeing here. These are fossilized sand dunes, if you will. This is a picture I took in Zion National Park. That's out on the outside of National Park. My students are up there. They got the cross bedding above their heads, but you can see the nice cross beds in the picture.